The first question, when we join two SQL tables, are we allowed to apply Cartesian product on two multisets? Yes. Multiset. Yeah. Multiset, remember in this situation, basically we treat duplicate rows as different copies. Although those rows, they have the same tuple values, but we treat them as copy 1, copy 2, copy 3. Okay, yeah. In that way, we just treat them as different elements. Then we do partition. We do a Cartesian product, the standard Cartesian product. So you have no problem doing that. Okay, yeah. Do not remove duplicate rows. Okay, yeah. Keep duplicate rows, but different copies. Okay, yeah. Next one. Is it possible for us to select a symbol other, yeah, backslash, to be used as the escape symbol? Remember, we use the escape keyword. We can define new escape symbol. Okay, yeah. Keyword. Okay, yeah, use that keyword. Pavan Kumar. Okay. Yeah, I'll check it. Yeah, all right. Yeah, so don't worry. Yeah. But it seems every time you need to define it, right? Yeah. Yeah. It seems not convenient because usually we like to have a default symbol, right? Yeah. Here it's a little different than what we usually do. Yeah. Number 3, if a SQL table does not have any primary key, it's possible, right? Yeah, it's possible. Is it possible for us to update a row in the, so it is here, it is possible, right? Possibility. Yeah. Answer is yes. Answer is yes. Yeah. So I explained this question a few times before. Yeah. So here we talk about possibilities. Okay. Yeah. The first situation we like to have, although there is no primary key, but we may have composite keys. Okay, yeah. So that's one, case 1. All right. Case 2. Case 2. Different. Couple values. Can be used to identify different rows, different tuple values. Yeah. Then case 3. No distinct. Oh, Yeah, we should not say in that. I should write this way. With duplicate. With duplicate tuple values. All right. Yeah. That could happen. Yeah. Then this case more complicated. Yeah. One way to do, use the row numbers. But this case, although you use row numbers, you can distinguish different rows for duplicate tuple values. Yeah, but still not easy to control different copies. Think about that. Okay. Yeah. So this situation is the hardest one. So you really need to pay attention. So for the case number 2, it's better you understand your business a little more. Here we're talking about some abstract assumption here. So because we do not have the business background behind it. Yeah. So if you have certain business background, so probably you can do better in this case number 3. Okay. Yeah. Yeah. But the basic idea, so using this row number to separate those duplicate rows. Yeah. But still, you need to handle the details there. Yeah. How to apply, in what way to control those row numbers. Still a big question mark there. All right. Yeah. Just to give you the possibilities. But the possibility number 3, that is the percentage very small. Yeah. That could happen, but the probability is very small. Number 4, yeah, so this one, I'd like to explain. Count. Here we use the count function. Yeah. So when we use the count function, there is a special property we need to consider carefully here. Yeah. A SQL table has several columns, C1, C2, Cn. Now we apply the count function on different columns of this table. Can we say that count for those individual columns always return the same number? The answer is no. Answer is no. Yeah. All right, so why? Yeah, the answer is very simple. The biggest reason no is that null value. Null value could occur in those columns, right? Yeah. Think about C1, C2, C3. Yeah, let me just use 3 columns. Okay, yeah. We know for different rows, the null values could be at different locations, right? Right? Yeah. Okay. Yeah. But when we call that count function, C, just any number, yeah, Cx, okay, represent one typical column. this function only count the numbers that are not null. All right, yeah. C1, for example, if one row has the null value somewhere, this function does not count it. Okay, it does not count it. Yeah. Remember, we did one example before. Remember, I remember I gave you one example, count super underscore SSN. Super underscore SSN. So that's one way. The second time, we still count the employee table, but we use star. These two ways, they return two different values. This one, you only count those employees whose super underscore SSN are not null. And this one, including those rows whose super underscore SN take the null value. The difference is 7, okay? The second one, 7 more than the first one. Okay, yeah, because there are 7 employees whose super underscore SSN take that null value. Yeah. So here in this question, yeah, we do not have the information to the null value, right? If I say all those rows, all those columns, they do not take the null value, then you can say that number is the same. Okay, if I give you that condition, no null value is allowed in those rows, in those columns. No null value is allowed. Okay, then you can say same. Otherwise, including the null value factor, different. Okay, all right. Could be, yeah, could be different. Yeah. Number 5. Yeah. In SQL statements, all the nested must be correlated. No, yeah, this is simple. Yeah. Because correlated, the inner query needs to refer to the outer query. That relationship should be there. Okay, yeah. But for some nested query, the inner query may not refer to the outer query. Yeah. For relatively simple queries, yeah, no relation, not correlated. Yeah. That's pretty easy for our understanding. Yeah. But for correlated, then we need to understand carefully. We need to, really follow the structure. So that structure, remember, for the outer query, we take one tuple, we call a tuple variable. Yeah, just like an iterator, just like nested for loops, we have an iterator variable from the outer for loop, outer loop, yeah, iterator variable. Here, we use the tuple variable concept. Right? So that's from auto query. All right, then when we move to the inner query, we fix it. Fix it. Then in inner query. In the inner query, we need to go through all the tuples in the inner query. But the outer query, that variable, for that iteration, we fix it. Okay, yeah. In that kind of understanding, so we will feel better. Yeah. Okay, yeah. Number 6, in SQL tables, all the aggregate functions must be applied to attributes with a total order. False, because there is one exception. One exception. Total order. Max, min, total order. Right? Some average should be applied on numerical values, right? Numerical values must have total order. Yep. So you don't worry. But there is one special aggregate function, count function. When we apply count function, we do not need total order, right? Think about it. We count the number of rows satisfying certain condition. Why we need a total order? We do not need to do comparison, right? When you count the number, you don't need a comparison. You don't, only when you need to do comparison, you need a total order. When you do not need to do comparison, you do not need a total order, right? No total order needed. You can always apply count function, but you may not be able to apply other aggregate functions. Max, min, sum, average, different properties. All right, number 7. If a table has composite key, then this table must be a set of tuples. True. This composite key condition, yeah. So you use multiple columns to define a composite key. We know those composite key, they have the property, unique values. Unique values with respect to those composite keys. When you have that property, then we have the conclusion, this table does not have duplicate tuples. Can you see it? Can you see it? Yeah. Let me draw a simple diagram to explain this conclusion. Suppose this is the whole table, okay? This is the whole table. So we have multiple fields, multiple columns, many rows. All right. Here, let us assume some composite key. So this is the composite key. Okay. Yeah. Composite. So that means if you just look at these, the values in these rows, unique values. Then look at the whole table. Unique couple values. Yes. Because you take any number of tuples, you only need to look at the composite keys. You just look at the segment on the composite key part, that segment already unique. When you focus on the composite key part, already unique based on the definition of composite key. Then you expand to the whole table must be unique, the values. No duplicate rows. Otherwise, contradiction against that composite key assumption. Think about that. Simple conclusion. Okay, simple conclusion. Okay, yeah. All right. Number 8. Yeah, so I need to erase. Okay. Yeah. All right. Yeah. When we compare two tuples, Smith, the second component null value in SQL, do we expect they have the same? They are no. The reason is simple. For different duplicate values, DBMS consider them with different values. Null value 1 is not equal to null value 2. The reason is very simple. Think about the reason. The reason behind, so you may ask why two null values are not treated as the same, because we know the null value temporary unknown, those values. And their real values could be fixed sometime later. Think about when you find out those unknown values later, it's very likely those values are different, right? Although there is a possibility they could be the same, but also there is pretty good chance they have different values. So that big possibility you need to consider. So in general, DBMS treat them as different values. So that's the simple reason. Yeah. So number 9, when we join two tables, we require that these two tables must be union compatible. Yeah. So here I try to get you confused. Answer is false. Otherwise, they cannot be joined. It's false. For table join, we do not need. For set operation, remember this concept connected to the set operations. We require union compatible. Otherwise, you cannot apply set operations. If two tables are not union compatible, you cannot do set operations. All right, yeah. But here, I try to confuse you. I replace that set operation by table join concept. For table join, we don't have that condition. For table join, we can always join two tables. No compatibility issue. You cannot say these two tables are not compatible, so we cannot join them. You cannot say that. No compatibility issue when you join two tables. Why? Why? The reason is also very simple. Why? You can always join two tables. Here. Why? We can always join two tables. The reason is very simple. Yeah. Because we can always apply the Cartesian product on two sets or multiset. When we apply Cartesian product, oh, I need to dismiss this side. Okay. Do we need to check compatibility? We do not need, right? Cartesian product. Yeah, think about it. A cross B. We do not have compatibility issue, right? Any two sets. So we can apply Cartesian product. Conceptually, we can apply Cartesian product on them. Okay, yeah. All right. So that's this concept. All right. Always cover. What is the value of the four? Yeah, that's easy. True and unknown. Here we use and. Think about it. And. True and unknown, the value should be unknown, right? Think about it. When you use and, that unknown one becomes the final value of the first parenthesis, pair of parentheses. Then look at the second. Use all unknown for the false, all unknown, all also unknown value, right? Think about it. False, but all. You use the all operator. So unknown could be true, could be false. When unknown is true, that all, you take the true value, right? Unknown is false, you take the false value. Here, and unknown is false, you take the false value. Okay, so both sides, you have unknown. Unknown and unknown, you take unknown and unknown, right? You take unknown. Yeah. Because it could be true, could be false. When both unknown true, you take true value. When one of the unknowns is false, you take the false value. then the answer unknown. Yes, could be true, could be false, unknown. Yeah. All right, so that's the 3-value logic in SQL. Yeah, okay, so you need to be familiar with, yeah, because sometimes it could be a little confusing. Yeah. Sometimes if I give you a relatively more complex Boolean expression, a little more complicated. Not, remember, I can also use not. The 3 operators, and, or, not, you know, mix them in different ways. Could be a little complicated. Yeah. All right, yeah, so that's quiz number 4. Okay, all right. Then, yeah, I'd like to, you know, give you a few more examples for query questions. Okay, query questions. Now, all right. Yeah, in this midterm, I plan to give you 5 query questions, not too many. Okay, yeah, 5. Yeah, and not too complicated, because in this midterm test, we do not work on relatively complicated queries. Because after midterm, we need to spend a little more time on complicated queries. Yeah. So we need to build up our experience on complicated queries after the midterm. And in the final, I plan to give you also 5 query questions, final. Okay. Yeah. But you need to practice a little more to have a little more experience for the final. Yeah. All right. Yeah. And at this point, actually, we do not have very complicated queries. Yeah. Yeah. Later, there is one type of queries that I treat pretty complicated. It uses double negation. Think about double negation. That type of one, very confusing. How to understand? You negate twice. Yeah, so you have a statement. In order to represent that statement accurately, you need to do negation twice. That type is very complicated, very hard to understand. Yeah. So double negation type queries. Yeah. So we will study that type after our midterm. Yeah. Right. The first query question. Display the first name and last name of the employees and number of dependents of this employee, so that this employee has at least one teenager child. One teenager child. So here, they represent teenager. So the age, right? Yeah. The age, teen, 13, between 13 and 19. That representation. Yeah. All right. And the children, dependents, another, not spouse. So you need to exclude spouse, only consider children. Then the birth date. The birthday comparing with the current date, right? Current date. So then the range for the ages. Yeah. So consider those things, you write the query. All right, so here, yeah. Correlated query. Auto query employee. That's simple. Then we fix that employee. We take that employee, each individual employee, we fix it. Then we get into the inner query. Yeah. Inner query, here we use this in operator. There are different ways. Yeah. So this is just one solution. You have other different ways to represent it. Here, another example to let you see this in operator very useful. Yeah. We can use it to write many nested queries. So E.SSN in, then we consider the inner query, select ESSM dependent table. First, the relationship different, not equal to spouse. That's easy. Then B date, between. Yeah. Here we use that between operator. Okay, between, inclusive, between, okay. Yeah. Current day minus interval 13. Yeah. So you define the interval, 2 endpoints. Left endpoint 13. Yeah, 20. Yes, so here. 20, 19, inclusive. Yeah. That, to be more precise, do you think should be 19? Yeah. Although here for our question, it's not a big deal, okay? So when you write 20 or 19, so I do not take point off. Okay? Yeah, because we just want to make it correct in the real world. Okay? Probably 19, right? Yeah. Because if we consider between inclusive, yeah, because 13 inclusive, right? Not inclusive. Why one side inclusive, the other side exclusive, right? Yeah, think about that. You know, at least it should be consistent, right? Yeah. So it's better put 19 there. Okay, inclusive between. Yeah. Yeah, because our between operator. Yeah. Yeah. Okay. Yeah. Small difference here. Yeah. Yeah. We should be a little careful here. Yeah. All right. Yeah. The first question. Second one. List the name and address for those employees whose addresses satisfy the condition. The street number has exact 3 digits, no non-numeric character. Well, because for some countries, their street numbers could be some non-numeric characters, right? Letters could happen, right? Yeah, possible. Yeah. But here, we just consider the digits. So you have to describe digits. You have to use the regular expression to describe digits. Okay? Regular expressions. All right, so here, just look at the regular expression. Street number start with that symbol, little wedge, that symbol, beginning with digits 0-9, just for 1 character, but you repeat that pattern 3 times, 3 characters, and with space, and with space. All right. Yeah. Yeah, this one is pretty simple, pretty straightforward. Yeah. But think about, I may modify this question a little bit. Yeah. For example, not exact 3 digits. between 3 and 5. How about that? 3, 4, 5, all okay. Yeah, in a range, 3 to 5 digits. Okay, yeah. So do we have a range expression like m comma n? Regular expression, start from m, end with n. Yeah. So you can use that way. Okay, yeah. Yeah. I remember we talked about that. Yeah. Simple range. Yeah. Okay, yeah. Next question. Find the average of projects per employee in the company. So this example, average, aggregate function average number, AVG, right? Aggregate function average. But this question slightly different from our usual aggregate function way. Think about our usual way to apply average function. One way we apply this function on the whole table with respect to a specific column. Another way, so not the whole table, we define subgroups and we apply this average function on each subgroup directly. So that's the usual way, but here it's different, slightly different. Yeah. So I like to show you this example. Different. So how different? Think about, do we have a table? We don't have such table where we can get an average number of projects for different employees. We don't have that table, right? Yeah. In our original tables, we don't have that kind of relationship. How do we connect the number of projects? Here, we need to connect the number of projects and the employees. But when you do that connection, you need 2 tables, not 1 table. If 1 table, we can apply AVG function directly, but 2 tables, then you need to do things a little different. Okay. The number of projects connected to employees that works on, right? Yeah. Works on. Oh, yeah, actually, yeah. Actually, yeah. So here, yeah, actually, we can use 1 table to get that information. Yeah. Yeah. So that 1 table is this works underscore on table. We can have that information. Okay. Works on. Yeah. But works on right. Yeah. Even that works on information. Yeah. Works on information. Yeah. You need to do operation. Yeah. All right. Here, let me show you the query here. All right. Oh, yeah. Here, the query average. We need to take division. Yeah. by the definition of area, we need to take the division. The numerator, the total number of projects, right? Denominator, the total number of employees. Then we take that division. That's the definition of average. Yeah. All right, so how do we get the total number of projects? From the works on table, we count the number of rows, because each row represents a project counted with respect to one employee. Right? Yeah. What's the meaning of one row in works on table? For each employee, one project that is worked by this employee. That project counted on top of this employee, that one instance. Okay, yeah. For the same project, many different employees work on that. We need to count many times, right? Yeah. Because we want to count the total number of projects worked by one employee. So here, look at it. The first number, we do not count the total number of projects. We count the total number of project instances worked by employees. Those two concepts are different. So here, the numerator, not the total number of projects. Okay, because each project is counted not just once, multiple times. Because a project is, there are multiple employees work on this one. And for those employees who work on this project should be counted that many times when we do this average. Okay, yeah. Yeah. All right. All right, so I hope you can see this picture well. Okay, yeah. Yeah. So basically for each employee, you have a number of projects that this employee worked on, you have that number, right? Another employee, you have, right, so here. So suppose this is employee table. Okay? Yeah, many employees. E1, E2, E3. Okay? Yeah. Now to do the average, for this employee, you need to count the number of projects this employee works on, let's say C1, right? Yeah. For this employee, you need to count the number of projects this employee C2 and so on. C3. Okay. Now, so the last one, let's say CN. Okay. Okay. All right. Then to do the average, you need to add up all these count numbers, right? Divided by n. Okay. Yeah. So here you can see each project is counted multiple times, right? Not once, many times, because there are many employees who may work on one particular project. Okay. Yeah. So this total count number, how to get this number better from works on table. Okay, yeah. So you count this work on total number of rows. That's this number. Okay, yeah, but you use a alias, WC alias. Oh, sorry. This alias. Okay, yeah. Then the second one, number employee from employee table. After that, select. You do that division. Yeah, you can do it in this way. Okay, use the alias. You can find that number. Yeah. So you can use the aggregate functions in this way. Yeah. Okay. So here you can see in this place, alias is very important. Yeah. All right. Yeah. All right. So next question. Retrieve the first name, last name of those employees who have no spouse in the company record. Spouse. Yeah. Some employees who may not have spouse in the dependent table due to any reasons we don't know. Okay, yeah. So we want to count. Look at the query. Yeah. Auto query, then fix that employee. Then we want to look at the inner query, not in. Here, not in. Yeah. All right, not in. In the inner query, we select ESSN. So we consider though the table of those employees who have spouse in the dependent table. Yeah. So we get that whole list. All the employees who have spouse in the dependent table. But the current employee does not belong to this table, that table. The logic is simple. So here you can see is not an in operator. So you can do it in this simple way. Definitely you could use different way. So the logic, based on your understanding, you have different solutions. That's normal. That's normal. But one thing, when you have multiple ways to write the queries, try to find a relatively easy way. Okay? Yeah. Easy for understanding. Yeah. All right. Yeah. The last question. Retrieve the name of those departments that have 2 or more locations. We have the department location table, right? Yeah. Yeah. But we need to look at the number of locations for all those departments. 2 or more, not just one location. Some departments could have multiple locations in our company database. So we want to look at those departments by names. So we need at least 2 tables, department table and department location table. All right. Auto query, DNAME, department information. Yeah. Very easy, so we fix that. We fix each department. Then we look at the inner query. Count. When we fix that department, we count the number of locations from department underscore location table, DL. Then look at the DL dot number equals D dot number. That count number should be greater than 1. Yeah. Okay. Yeah. Simple. Yeah. Also pretty simple. Yeah. All right. Yeah. Yeah. So based on the simplicity, so you can see most of these questions about nested, correlated queries, and a few about regular expressions, and a few about aggregate functions. All right, so here, for the midterm, the 5 questions, okay, 5 questions, 5 query questions. In midterm. All right. 1 about regular expressions. Second, about aggregate functions. Co-related queries. Yeah. 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 Basically, in that way. Okay. Yeah. But not too complicated. Similar to these 5 questions. Yeah. The difficulty level similar to these 5 questions. Okay. Yeah. All right. Yeah. So when you do preparation, yeah, just control in this way. Okay. And in the midterm, in the final, we will do a little harder than these 5 questions. A little harder, but hopefully not too much harder. All right. So that's for our review number 3. Okay. All right. So let me stop right here.